So as we promised, today we are going to show you how Midas Civil is a special software for post-tensioned segmental bridge design. And this is our agenda today. I hope you can see the screen just changed to agenda, and it says this is the agenda that we are going to talk about today. We'll talk about why finite element analysis is required for segmental bridges. What are the typical modeling issues with finite element modeling of these type of bridges, and how Midas Civil can help you to set up the model, how Midas Civil can help you in precise analysis, and then we'll see how you can do the automated design as per the latest ASHTO code, ASHTO LRFT. And for those who are connecting us from Canada, we can also do the pre-stressed bridge design as per the Canadian code, so it's not a limitation with Midas software. And finally, I'm going to show you the design optimization for segmentally constructed bridge in Midas Civil. The last part of this webinar is going to be pretty interesting, so I request you all to be in the webinar as long as they can be. So first of all, let us see why finite element analysis is required for segmental bridges. Now first of all, whenever we construct a bridge, it requires a lot of money. The design, the construction, everything requires a lot of money. And since the segmental bridges are generally long span bridges, they are massive bridges, they would require more money, and we don't want anything to go wrong. And since finite element analysis is the most precise solution out there for bridges, we need to analyze them carefully, and thus we need to choose finite element analysis. Now, we know that these bridges are constructed in a finite amount of time, and since they are pre-stressed, there is a loss of pre-tension while we construct the bridge and after the bridge has been constructed, and these effects have to be carefully evaluated. The loss of pre-stressing and the secondary effects of pre-stressing, they have to be carefully calculated, and the best option for us is to perform a finite element analysis with the help of a software. Yes, you can also use hand calculations, but the program gives you more precise results and it is quicker. The time-dependent material behavior of concrete must also be studied for these type of bridges, because as I said earlier, they are completed in a finite amount of time, and we want to make sure that the camber or the connections that we are designing for this bridge are fine, and thus we need to consider the time-dependent material behavior so that we can obtain the required camber and the geometry of the bridge. The construction loads need to be considered in analysis for these type of bridges, and since the bridge completes in n number of stages, there are different construction loads in different stages, and that's why finite element analysis is a more practical approach in this case. And once again, since they are large span bridges, and hence the seismic evaluation with refined methods is necessary. So these are some of the reasons why we need finite element analysis for segmental bridges. Apart from these factors that I've already talked about here, there are several other factors that we need to consider for segmental bridges. The moving load analysis, it is more precise if you do it with finite element analysis. Similarly, the performance-based design and stuff like that, we need to perform it using a software by performing the finite element analysis. So these are some of the reasons why we need to perform finite element analysis to design post-tensioned segmental bridges. Now going ahead, let's talk about the typical modeling issues with finite element modeling of these type of bridges. So I'm not talking about Midas Civil here, I'm talking about any finite element analysis software that you must be using to model these type of bridges. So the first and foremost is, we know that the post-tensioned segmentally constructed bridges they generally have the varying depth of the girder with the length of the bridge. As you can see in these examples here, they are bridges constructed using balanced cantilever approach, and you can see the depth of the girder is maximum at the mid-span to cater for high hogging bending movements at these locations. And as you move away from the mid-support region towards the mid-span region, the section depth reduces. So in order to save the concrete, we need to do this kind of profiling of the bridge. And if you think about it, the balanced cantilever bridge, it has high cantilever ends, and it will have high negative bending moment or hogging bending moment at the mid support region, which required the depth of the girder to be very high at the mid support, and it doesn't require that much depth at the mid span region. So when we are modeling this type of bridge in any finite element analysis software, we need to define a lot of cross sections at all these locations. So this is one of the issues when we are modeling these type of bridges. Now secondly, as we know, these bridges are post-tensioned or pre-stressed. We need to define the tendons in finite element analysis software. Now I've shown you the example of pre-stressing in post-tension segmentally constructed bridges with the help of an animation and the midas civil model here. And you can see that we need to define a lot of tendons. Now defining the geometry of the bridge is not that difficult, but defining each tendon is a tedious task. And this bridge is straight here. If we have a curve in the bridge, which generally is, we need to make the tendons along the curve, which is again a very tedious task. So defining a large number of pre-stressing tendons, modeling them, it requires a lot of effort and time. Now, since we know that these bridges are constructed in several stages, we need to have different tendons in different stages, and hence we need to define these tendons in individual stages. And again, it's a tedious task. Now, there are different types of bridge construction methods of the bridge. It can be balanced cantilever type of construction, span by span type of construction, or incrementally launched type of bridge construction. And when we are working with these type of bridges, when we are designing these type of bridges, it is important that we model the construction stages for this bridge so that we can define the additional load which is on the bridge during the construction stages, and at the same time we can make sure that there is no critical failure in one of the construction stages. So we need to define the individual construction stages for these type of bridges. To demonstrate the construction stages, I have created a small video. So I'm going to share the video with you now. So this is the video that I have created for the bridge constructed using balanced cantilever approach. You can see this is a cast in place balanced cantilever bridge. You can see how the concrete is being poured in the scaffolding and in the formwork, and the scaffolding is all around it, and once the concrete hardens, the scaffolding and the formwork is moved along the length of the bridge, and this is how this bridge is constructed. So if you want to simulate this kind of construction methodology for this type of bridge, you need to have a lot of construction stages in the software. So again, it's a tedious task. It requires a lot of time and effort to do this. Okay, I'm just trying to open the PPT again. It's taking a little time, so please bear with me for a minute. Just give me a second. I guess it's messed up somewhere because of the video, but I need to open the presentation again. Okay, it's just done. I'm sorry for the delay. Okay, so we are back. So I just demonstrated to you how the balanced cantilever bridge is constructed, and the idea behind showing you the video is so that you can see how the bridge is constructed and how you have to create the individual construction stages for this particular bridge type. Now let's talk about the incremental launching method. This is how the incremental launching method is completed. You can see that on the very left there is a casting bed where all the elements are casted, and then once the element is casted and it has hardened, it is pushed along the bridge. So this is how this particular type of bridge is constructed. We cast the element at the casting bed and we keep on pushing it towards the length of the bridge, and at the front we have a launching nose which controls the deformation, and the piers are constructed already, and we have the launching bearings and lateral restraint at each pier, and once the bridge erection is complete, we replace the temporary bearings with the permanent bearings. So this is how the incremental launching method works. Now the span by span construction method for these type of bridges is fairly simple to understand. In this type of construction method, an individual span is constructed, and so as the method name is, the bridge is constructed span by span. So the idea behind telling you these type of construction methodologies is because I want to tell you that in any software that you are working with, you need to artificially simulate these kind of construction stages so that you can obtain the precise effect in individual construction stages. The individual construction stages that you have in the bridge, they should not be critical, and that's why we need to perform a staged construction analysis. And at the same time, we need to obtain the camber for bridges constructed using balanced cantilever approach, and that's why these construction stage modeling is important. Now when we construct the bridge in different stages, the erection loads at those times are important. So here you can see in this picture that there's some scaffold, there are some people standing on the bridge girder itself, there would be a crane, and if it is a cast in place system, there would be a formwork. So these are additional loads which we generally do not consider in the final model. So when we are performing the construction stage analysis, we need to consider these loads also. So this is again difficult to do in any finite element analysis software, because as the stage increments, these kind of additional loads, they have to be defined at different locations. So if we just talk about balanced cantilever bridge, as you keep on adding each new segment, the additional load will keep on moving from one location to another. So we need to simulate this particular loading type. And once again, these are the erection loads. You can see the crane and how the crane is holding the segment. So basically, if you see the scenario, the crane load is applied onto the top of pier itself. So through pier table, it is transferring to the pier, and all the segments which are hanging from the crane, their load is also transferred into the ground using the pier table and the pier. So the pier will have additional axial loads in this construction stage. So this is why we need to define the erection load or the construction stage loads while we perform construction stage analysis. Now sometimes we also need to have temporary supports while we are constructing the bridge, as you can see in this particular example. And when you are doing the construction stages, you might need temporary supports at different locations at different intervals of time, and once again they have to be modeled manually in any finite element analysis software you're using. So these were some of the issues, some of the modeling issues that we need to take care of while we are doing the finite element modeling of bridges constructed using segmental approach. And now I'll show you how Midas Civil can help you to set up the model. So basically in Midas Civil we have several modeling tools that you can choose, and they will help you to create these type of models very easily. Now first of all, let us talk about the balanced cantilever construction method, which is the most popular out of the incrementally launched and this particular method. For this particular construction type, we have developed a wizard in Midas Civil that can do the modeling. It automatically creates the geometric model of the bridge. So basically, based on the parameters that you define in the wizard, it will automatically generate the bridge model for you. It generates the 3D tendons automatically, so you don't have to manually define the tendons at individual location. Midas Civil will automatically define the 3D tendons for you. The construction stages are automatically generated, so you don't have to manually define each construction stage. We know that these are typical construction stage, but the program doesn't. So Wizard, it's intelligent enough to know what should be the construction stages, and thus it automatically defines the different construction stages you need in the model. And the loads, the erection loads or the construction loads that we need, you can define them in the Wizard, and the Wizard will automatically change the location of the construction loads as per the model progresses. And the Wizard is not a black box. If you want to make the changes once the model is generated, you can do that at any time you want. So these are some of the merits of using the Wizard in Midas Civil. Now I'm going to show you the Wizard itself and how it works. So this is how the Balanced Cantilever Bridge Wizard works. This is how it looks like. You can see that you need to define the material for the bridge, how many piers it has, and what is the stage duration. Then you need to define the pier section and what is the method of construction, whether it is cast in or precast. There will be a difference between cast in and precast, because if it is cast in, then the wet concrete load will be taken by the immediate element, which is right in front of it. And if it is precast, then it will be just brought to the site, and it will be connected to the bridge, and post tensioning will be done. So that's why we have provided this method of cast in or precast. Then you need to define the pier table. Depending on the pier table that you have, you can define a variety of pier tables in Midas Civil. Then you need to define the number of zones. So basically, as you can see in this Wizard itself, these are the zones that we have. So the zones depict how the balanced cantilever bridge will be constructed. So let's say it is, let's say on the left hand side of this particular pier table, let's say it is 60 feet long and it is constructed in 12 stages. So each zone will have a length of 5 feet, and there's gonna be 12 zones. So this is how you define the zones in the Wizard. In the second tab, we define the cross section. Now the cross section can either be the simple cross section as I have shown here, or you can define your own cross section depending on the type of bridge that you are modeling. So you have two types here, type 1 or type 2. In type 1, you can select the built-in cross section that you have in the model, but in type 2, you can bring in your own cross section. Now in the third tab, you will define the typical location of the tendon in different segments. So as you can see here, you will define the typical locations. And once you define these typical locations, Midas Civil will automatically generate the tendons for you. Now I would like to show you how Midas Civil Wizard works in Midas Civil itself. So I'll open a Midas Civil model and I'll show you how you can use Midas Civil to generate the geometric model of a bridge constructed using balanced cantilever approach. So this is how the work window of Midas Civil looks like. I hope most of you are familiar with it. On the top we have the menu bar. It's a ribbon menu bar. On the left hand side we have the works tree. Now the works tree is important because it lists up everything that you have done in the project so far. So you can see here that I have just defined two materials. I have one cross section for the pier, and I have defined the tendon property. Now I'm gonna go to structure and I'll go to the balanced cantilever bridge Wizard, and this is how it looks like once again. So I can define the number of stages, the number of piers, stage duration, the method of casting, and then I'm going to go to the section tab. I'll define the section dimensions, and I'll go to the tendon tab, and once I click on OK, Midas Civil will automatically generate the bridge model for me. So I just clicked on OK. It's going to take a second, and after it you will see that it has automatically generated the bridge model for us. So it's done, it's complete, and this is how it looks like. So you can see that in like a couple of seconds, Midas Civil Bridge Wizard has generated the bridge model for you. Now this is a straight bridge, as I said earlier, but if you want to model a curved bridge, it is also supported. You can just check on this option and you can tell what is the radius of curvature and whether it is convex or concave. and this way you can model the curved bridges in Midas Civil. So it's pretty simple, quick and efficient, and as I said earlier, Midas Civil will automatically generate the tendons for you. So now let me just activate the tendons. So this is how the tendons look like. So you can see a lot of tendons are automatically defined by the program. It's a bit difficult to visualize the tendons here. So let me change the color of the tendons. You can change the color of any item in Midas Civil very easily. So I'm going to go to color, and I'll go to tendon color, and I'll change the color of tendon from blue to, let's say, dark red, so that we can easily see the tendons in the model. And this is how it looks like. So once again, I'm redrawing the tendons for you. So you can see these tendons are automatically generated by the program. I haven't defined any of the tendon manually. If I zoom in at one location, you can see the tendons are defined by the wizard itself. So this is how it eases your work. Now I just undisplayed the tendons. Now as I said, Midas Civil will automatically generate the construction load for you. So if I show you the form traveler load, this is how it looks like. Now you must be wondering why is it on all the locations of the bridge, but it is not. It is based on the construction stages, which are automatically set up by the program. So if I go to CS1, this is how it looks like. Construction stage 2, 3, 4, and as you can see, the form traveler load, it keeps on moving as per the construction stage. So this way the wizard automizes the process of your work. It automatically generates the model for you. Now towards the end of the session, I'm going to talk about how you can use the bridge wizard to do the optimized design for these type of bridges. So for now, let us go ahead and see how you can do the manual definition of different items in Midas Civil. Now this is how the wizard works. This is how you can use the wizard to generate the model. But let's say you don't want to use the wizard and you want the bridge geometry such that you just want to model the bridge by yourself, and let's see how Midas Civil can help you there. Now first of all, Midas Civil can automatically calculate the effective width scale factor as specified by H12RFT and is being used in many countries, and this way you can obtain the effective stresses in Midas Civil. Now let's see how we can manually define the tendons in Midas Civil. To define the tendons in Midas Civil, you have two options. Either you can define the tendons by punching in the coordinates of the tendon, or you can import the tendons from AutoCAD. So both these methods are available in Midas Civil. First of all, let us talk about how we can enter the tendons by punching in the coordinates. So this is an example for the same. Here you can see that I have defined the coordinates in 2D, and this way I can define the XY and the XZ profile of the tendon. You can also select the 3D option, and then you can define the tendon in 3D. But for different type of bridges, we have different type of reference axes that you can choose from. We have three different type of reference axes. It's straight, curved, and element. Now the straight one is used when the bridge is straight. If the bridge is curved, you can use the curved reference axis, and then you can define the tendons as per the curved coordinate axis. But if the bridge has a reverse S-curve, or it is curved at several locations and then it is straight, then you can use the element reference axis, where you can define the tendons as per the centroid of the elements, and then as the elements move, the tendon also moves with it. So this is how you can use the tendon definition function of Midas Civil to define the tendons, and it's pretty easy. If you are working with reverse S-curve bridge, also you can use these type of reference axes to define the tendons easily. Now let's say some of you might be wondering how to define the tendons in inclined webs. which is one of the most difficult tasks when you are defining the tendons for these type of bridges. So if you have an inclined web in Midas Civil, it's very easy to define the tendons there. So what I will do is, first I'm going to define the tendon in the centroid of the girdle like this, and then I will give it a rotation angle and an offset. So I just defined the tendon along the centroid, which is pretty easy to do. Then you can just provide it a certain angle and an offset. So this is how you will do it. So if you have an inclined web, it's pretty easy to define the tendons again in Midas Civil. And as I said earlier, you can also import the tendons from AutoCAD. So as we discussed earlier, we need to have a different depth of the cross section at different locations in the bridge for these type of bridges. Now in Midas Civil, again, we have automated that process. Either you can use the wizard to automatically generate it, or if you want to do the manual modeling of the bridge, then you can use this function which automatically generates the tapered cross section for you. So now let me demonstrate this to you with the help of Midas Civil model itself. So I'm going to open a Midas Civil model again. So this is the Midas Civil model that I'm going to be using to show you how the auto generation of tapered cross section works. So for that, I'll go to structure, I'll go to PSC bridge, and I'll go to section and reinforcement, where I can define what is the section for the spans. And here I'm going to select span 1. As you can see, there are 2 spans in this particular bridge, and I'll define the reference line and what is the dimension. So I want the dimension to be increased from 10 feet to, let's say, 18 feet. So S1 is the support 1 for span 1. So this is S1 here, and S2 is the support 2, which is the mid support at the pier. And once I click on OK, you will see that the program has automatically generated the tapered section for you. So I just clicked on OK, and it's going to take a few seconds, and it will automatically generate the tapered section for you. So it's complete, and this is how it looks like. So I just created the tapered section for span 1, so that is why we just have the tapered cross section in span 1. But if you want to generate the tapered cross section in span 2, you can also do that using the same approach. So you will go to section and reinforcement, and you will select span 2, and this way you can generate the automatic cross sections, the tapered cross section in Midas Civil. Now moving ahead, let's talk about the span by span construction method. Now this construction method is one of the most widely used construction method, and let's see how Midas Civil can help you here. So once again, for this particular bridge type, Midas Civil has developed, we have developed a wizard in Midas Civil, and it automatically generates a bridge model for you. Here you can see that once again, in the first tab, you need to define the geometry of the bridge, what is the span of the bridge, and if it is curved, you can check on the radius, and you can define the radius of curvature, and whether it is concave or convex can be defined. In the second tab, you can define the cross section. Once again, you can either define the built-in cross section in Midas Civil, or you can import your own cross section. You can change the cross section dimensions here. And in the third tab, you can define the tendons. So here you can see how the typical tendons are defined in Midas Civil. And before I talk about the incremental launching method with you, let me demonstrate to you how Midas Civil Wizard works for span by span construction method. Okay, so once again I have opened a new window of Midas Civil, and here you can see once again I just defined 2 materials, 1 cross section and tendon property, and nothing else is being defined is in this model so far. What I'll do is I'm going to go to structure, and this time I'm going to go to span by span construction wizard. As you can see here, it asked me whether it is a tapered whether the profile of the bridge is tapered or not. If it is not, I can just check it off, and then I can define what is the cross section and what is the location of typical tendons. And once I click on OK, Midas Civil will automatically generate the bridge model for me. So I just clicked on OK, and here you can see this bridge model is automatically generated by the program. And once again, as I've shown you already, it generates the loads, the supports, and the tendons. So if I right click and go to display, you can see this is how the tendons look like. I need to change the default setting of this particular computer. The color should be red so that we can easily see it. So let me just change it again one more time, and you can see the color of the tendons in red. So this is how the tendons are defined automatically by the wizard, and the construction stages are also automatically defined. So this is stage 1, span 1 is constructed, stage 2, stage 3, stage 4, and stage 5. And for this particular type of bridge, since we have a cold joint at several locations, we can define what is the location of cold joint in the wizard itself. Now let's say I want to do any modification in this particular bridge. Once it is modeled in the wizard, I can go ahead and do any changes that I want to do in this bridge model. So it is as good as creating the model manually. You can do any changes. So you can, if you are working on a bridge model which you think will not be cannot be modeled by wizard, you can model parts of it with the wizard, and then you can manually fix the bridge model. So you can use it as an aid. You can use it to model the final bridge model for you. So this is how the bridge wizard works for span by span construction method. Now let's talk about the incremental launching method. So once again, this is how the bridge constructed using the incrementally launched approach is constructed. And moving ahead, we have a wizard that can automatically model this bridge. So for geometric modeling, this is how the wizard looks like. You define the bridge parameters like materials and number of spans, and what is the duration of each stage, what is the age of any individual segment, and then you define what is the location of top and bottom tendons as well as the web tendons. So once you define these typical location of the tendons, Midas Civil will automatically generate the bridge model for you, and then you define how the bridge is launched using this wizard. So this wizard, in this wizard you can define how the bridge is launched, and once you use this wizard, Midas Civil can automatically generate the construction stages for you. So this is how you can easily generate the geometric model of any bridge constructed using segmental approach in Midas Civil, but you are not limited to use the wizards. If you want to model the bridge by manually by element approach in Midas Civil, you can still do it. So wizards will help you, but if you want to model the bridge by yourself manually, you can still do it in Midas Civil. So it's not limited. You are not limited to use the wizard. You can still go by manual modeling if it pleases you. Now let's see how Midas Civil will help you in precise analysis. So that was all about the modeling part, and modeling is important, but at the same time you need to have the software which can perform precise analysis for these type of construction techniques. So first of all, as I discussed earlier, these bridges are constructed in a finite amount of time, and concrete gains strength in a finite amount of time again. So generally concrete gains strength in 28 days, and in Midas Civil you can consider the change in modulus of elasticity of concrete depending on the element age. So you can see, let's say it is a precast segment, and you transported the segment from the plant to the bridge site in, let's say, 10 days. So this would be the strength of that particular segment, and since the strength is less than the actual strength, I mean the design strength, it's gonna have the lower modulus of elasticity. So lower modulus of elasticity results in higher deformation, and we need to make sure that the deformation in individual stages are under check for these type of bridges, and hence we need a software that can do this kind of analysis. A software must always take into account the age of the member to obtain the precise modulus of elasticity to perform the analysis. Since these bridges are constructed or made of concrete, and concrete has creep and shrinkage behavior, we need to consider this behavior while performing the analysis on the bridge. Midas Civil can automatically generate the creep and shrinkage parameters for a variety of codes, and here you can see how I have generated the creep and shrinkage for the ASHTO code as per the ASHTO code. And the studies show that the code CBFIP is more precise to evaluate the creep and shrinkage parameters of the code. So that's why we have implemented CBFIP code too. So it's on your discretion if you want to use the ASHTO standard or if you want to use the CBFIP code to define the material properties. And this is how you can automatically do it. So for defining the creep and shrinkage parameters, we have ASHTO, ACI, as well as CBFIP, the latest version as well as the older version. So whichever version you are comfortable with, you can use that version to define the creep and shrinkage parameters for concrete. Now the effect is, let's say we are constructing a balanced cantilever bridge and there are two piers. So we'll start doing the construction in the cantilever form. So if, let's say, there is a delay in construction of pier 2 than pier 1, then it might happen that at the location of the key element there is more deformation in one of the flanges than the other. So this way, if you are using a program that can precisely evaluate this difference, you can adjust the camber so that the bridge has a perfect geometry at the end of the construction. So once again, you need to consider this. It is a precise analysis technique, and that's why we have implemented it in our software. These bridges have a lot of tendons. The post-tensioned segmental bridges, they require the tendons, a lot of tendons, and that is why, since they are indeterminate structures, we need to consider the secondary effect of prestressing, which Midas Civil can give you. So you can obtain the secondary effect of prestressing if you are working with Midas Civil. You can also do staged post-tensioning. So here, if you want to pre-stress a tendon once or twice or thrice while doing the construction, you can do that in Midas Civil, and you can also obtain the losses due to staged post-tensioning. So let's say in this example I've shown you there are two tendons, tendon 1 and tendon 2. The first tendon is pre-stressed in stage 1, let's say, and then a new segment is added, and the second tendon is again pre-stressed. Now these both tendons are post-tensioned, but due to the second tendon, the first tendon will have some elastic deformation loss, and Midas Civil can precisely calculate what is this elastic deformation loss in the first tendon. I forgot to mention that if you have any questions, you can put in the questions in the GoToMeeting control panel, and towards the end of the session I'm going to talk about, I'm going to give you the replies to the questions. So please feel free to post in the questions, and we will talk about the questions later during the seminar. Okay, now in Midas Civil you can also perform soil structure interaction. So if the bridge has to be constructed in soft soil region, you can perform soil structure interaction, and as per the ASHTO LRFT, it is mandatory to perform soil structure interaction and consider the elastic foundation for the seismic analysis. In Midas Civil we have this built-in feature where you can model the supports, and then you can define the soil parameters. As you can see on your screen, you need to define the soil type, the ground level, the pile diameter, the unit weight of soil, and these are the factors that you can obtain from the geotechnical engineers easily. And then Midas Civil will automatically generate the pile spring support for you based on the Matlock and Resi formulae, which is widely used by structural engineers to perform soil structure interaction. So this is once again a more precise analysis method that we have in Midas Civil. it depends on the soil type. If you are working in soft soil conditions, you need to consider this, and when you are performing the seismic analysis, AASHTO specifies that if the foundation is elastic, you need to consider it because it can change the demand in the event of an earthquake for this particular bridge type. Now let's see how Midas Civil helps you to obtain the precise results. Now whatever I talked about right now, it was all about defining some parameters for performing analysis. But how Midas Civil gives you the results so that you can use the results to do the actual work, the design work. So it is one of the most critical aspects of any finite element analysis software. Now let us see how Midas Civil gives you the results. So first I'm going to talk about the results in this PPT format, and then I'm going to show you the results in Midas Civil itself. So this is it. When we perform the construction stage analysis, Midas Civil gives a comprehensive result table or comprehensive result description in this following format. So it gives you the CS dead load. So whatever dead load you have in the structure, like the dead load of components, etc., it will be given by the program under CS dead load. The CS erection load is any construction load that you have, and it gives you under CS erection load. The tendon primary is the primary effect of prestressing. The tendon secondary is the secondary effect caused by tendon prestressing in the indeterminate structure that you can obtain from Midas Civil. Creep primary is the primary effect of creep of concrete. Creep secondary is the secondary effect of creep, because once again it is an indeterminate structure and there will be some secondary effects of creep that you can obtain from the program. Similarly, you can obtain the primary and secondary effect of shrinkage. So basically, if you talk about a beam which is fixed support at two locations, and the concrete will shrink, but since it is fixed support at the two locations at the two ends, it is not allowed to get shrunk, and it will induce some forces inside the beam, and these are the secondary forces that you can obtain from Midas Civil. So this way Midas Civil gives you detailed results for construction stage analysis. Now talking about the stresses, you can obtain the stresses in Midas Civil at several locations for different components. So this is how it looks like. So here you can see there are different positions at the cross section where you can obtain the stresses. 1, 2, 3, 4, depending on where you want to obtain the stress. And if you want to define the stress point yourself, you can also do that. And there are different components that you can obtain the stresses for. You can obtain the stress for axial force, the stress due to bending in X and in Y and Z direction, the torsional stress, the shear stress, and you can also obtain the stress in the principal axis. So it's pretty comprehensive for post-tension bridges. Midas Civil also gives you the initial tangent displacement of erected structure. So in this example, I've shown you what it means. So let's say this is the deformed profile of a bridge. It's a highly exaggerated deformed profile of the bridge. Now, if I want to have a new segment, this is how the segment will be erected or casted, and it will have an inherent deflection due to the rotation of the joint where it has to be connected. So if you want to obtain this type of deformation in Midas Civil, we have this option that you can check on while performing construction stage analysis. It is known as initial tangent displacement for erected structures, and it gives you precisely what is the deformation of the element due to this effect. Since all these bridges which are constructed using segmental approach are pre-stressed, we need to assess the tendon losses. And once you perform the time-dependent material analysis in Midas Civil, you can obtain a comprehensive tendon loss table which gives you the stress after immediate loss, the elastic deformation loss, it gives you the loss due to creep and shrinkage of concrete, and it also gives you the relaxation loss. The relaxation of tendon can also be defined, and it gives you the relaxation loss accordingly. So this is how Midas Civil will help you to obtain the losses in the tendon. Now moving ahead, moving load analysis is also important, and Midas Civil can do it for these type of bridges. You can obtain the camber automatically. You can see that you will ask the Midas Civil program to give you the camber for different stages, and this is how the camber looks like. You can see it tells you what should be the camber for individual stages, and finally at the end of construction all the values become 0, which implies that we have achieved the final profile of the bridge. So this is how you can obtain the camber from Midas Civil automatically for these type of bridges. And you can also perform seismic analysis in Midas Civil to obtain the demand in the event of an earthquake. You can perform the elastic dynamic analysis or response spectrum analysis. The response spectra can be automatically defined by the program. To evaluate the capacity of the structure, you can perform pushover analysis. You can define the hinges at several locations, and then you can perform pushover analysis to obtain the capacity. If you want to perform boundary nonlinear times tree analysis, if you have boundary nonlinear elements, then you can perform boundary nonlinear analysis in Midas Civil. And you can also perform a full-fledged inelastic times tree analysis for long span bridges in Midas Civil. So you can see that you can specify what is the load versus time graph for the earthquake, or displacement versus time graph, and you can obtain the effect of what would be the response of the bridge in the event of an earthquake. So all type of seismic analysis which can be available in any type of finite element analysis software can be done in Midas Civil. So this is how it helps you. So before I talk about the automated design of pre-stressed bridges or post-tension segmental bridges in Midas Civil, I'm going to show you some of the result features of Midas Civil with the help of the model that we just generated. So I'll just open the model for you, and I'm going to show you how the results look like. So this is the model that I generated using the wizard, and here you can see that for this particular bridge model the analysis has been complete, and it took about 60 seconds to perform the analysis, so which implies the software is pretty quick. The analysis speed is pretty quick. Now let us see the results in individual stages. So let's go to stage 1 and let's see what is the deformation in stage 1. You can see the deformation for a variety of load cases. Here I'm selecting dead load, and this is how it looks like. So if I keep on scrolling, you can see how the deformation looks like. Once again, these deformations are not the initial tangent. They do not consider the initial tangent displacement, because I haven't considered the initial tangent displacement option here, and I wanted to demonstrate to you the software analysis speed. So I'm just going to do it right now in front of you. So I'll just perform the analysis and it will complete the analysis in no time. So just to demonstrate the analysis speed for the balanced cantilever bridge that we have here, I have run the analysis in front of you. So it's going to take about a minute to perform the analysis, and you can visualize that the solver that we are using in Midas Civil, it's pretty quick because it works on the multi-processor platform. And right now it is performing construction stage analysis, which is about 60% complete. Then it's going to perform the static analysis and the moving load analysis. It is important that the software that you are using must have a good analysis speed, because even if it gives you precise solutions, if it takes more than a day or 2 days to run the analysis, it is impractical, because I'm pretty sure you would not be confident while working in this scenario. And here you can see Midas Civil, it performs analysis pretty fast and it is complete. So as you can see on your screen, it took about 68 seconds to complete the analysis. And let us see the results again. So I'll go to stage 1. Let us see the deformations. We'll again see the deformation due to dead load, and this time I'm going to check on the stage step real displacement, which tells you what is the deformation based on the initial tangent displacement. So if I go to stage 5, this is how the deformation look like. Stage 10, this is how the deformation look like. So this is the deformation for the dead load. If you want to obtain deformation due to tendon primary, this is how it looks like. And if you want to obtain the tendon considering both prestressing and dead load, then you can select CS summation. If you want to obtain the deformation due to creep and shrinkage, you can select CS creep and CS shrinkage. Now let us see the stresses. To see the stresses, we'll go to stresses, beam stresses, and this time I'm going to check off the deform. I'll obtain the stress at position 1 due to axial force, which is going to be very low in this case because there is virtually no axial load. Let us see the stress due to moment. This is how the stress looks like. For dead load, this is how the stress looks like. If you want to see the stress for tendon prestressing, you can select the load case as tendon prestressing. This is how it looks like. So the tendon will induce the axial stress as well as the stress due to bending. So we can obtain the axial stress and bending stress after defining the tendons in this particular model, which are already defined by the program. Now let us see the beam diagrams. So let us see the beam diagrams due to dead load in this stage. This is how the bending moment diagram look like. If you scroll to different stages, you can obtain the bending moment diagrams for individual stages. So this is how you can obtain the results in Midas Civil. So let us go to the final constructed mode now, and let us see the results due to moving load analysis. So to obtain the results due to moving load analysis, you can go to MV max moving, which gives you the maximum sagging bending moment envelope. If you want to obtain the maximum hogging bending moment envelope, you can go to MV min moving, and this is how it looks like. And if you want to obtain the location of the vehicle which produces the maximum effect on any member, you can use the moving load tracer, and this is how it looks like. It gives you the location of the truck for the maximum or minimum bending moment, shear force, axial force, torsion at any member. So this is how you can obtain the results from Midas Civil. Now if you want to obtain the tabular results, it's pretty simple. You just go to, let's say I want to obtain the bending moment diagrams. The bending moment in the tabular form. I can go here. I can select for what element do I want to obtain the tabular results. Let's say from element 10 to 20. And I can select on what part do I want to see the results. And once I click on OK, Midas Civil will give me the tabular results. Now these tables can be copied to Excel, or you can export them to Excel too. If you want to change the units here, you can change the units after you created the table, and it gives you a dynamic response and it changes the tables automatically. So this is how Midas Civil can be used. If you want to obtain the camber, just go to camber control and obtain the camber for this bridge construction method. So this is how Midas Civil gives you the results. It's very comprehensive. It is more comprehensive than any other finite element analysis tool that you will work with, and that's why we recommend Midas Civil for post-tension segmentally constructed bridges. Now let's see how the design can be automatically done by Midas Civil. For that, first I'm going to show you the presentation in which I have listed what are the different design aspects that Midas Civil caters to. So here you can see, you can check the stress for cross section at construction stage, then you can check the tensile strength for pre-stressing tendons, you can also check the flexure strength, shear strength, and you can check the combined shear and torsional strength in Midas Civil. So once you perform the design, Midas Civil can also give you the Excel compatible tables, and it can also generate a full-fledged Excel report for you, which gives you the different formulas which have been used in the program and how these values are calculated. So this is how Midas Civil gives you the design results. Now I'm going to show you the design result for this particular model that we are working with. So let me share the design results with you. So when I go to PSC, I can select the code as H2LRFT 2012 or 2007, and I can also select the Canadian code, the latest Canadian code. Now if I go to result tables, I can check the flexure strength, and the location where it is not good, it writes NG. It literally writes NG, which is used by engineers all the time when the section is not good, and it shows the color as red. So you can, just by looking at this table, you can see at which locations it is not good. Similarly, you can obtain the result for shear. This is how the results for shear look like, and you can obtain the stress for cross section at different locations. You can change the units at any time you want. So I just change the unit from kips feet to kips inches, and you can obtain the principal stress at different cross sections. So basically it gives you what is the stress at different cross sections and what is the allowable stress as per the code, and then you can make sure that your design is okay as per the code. So these are the basic items that you have in Midas Civil for the design of post-tensioned segmentally constructed bridges. But now let's talk about the most important aspect of why we have these wizards for you. These wizards will help you in doing the optimized design, and now I'm going to talk about the steps that you will follow in Midas Civil to do the optimized design. So first of all, let me talk about the conventional post-tension box girder design process to you. So first we do the preliminary design, we do the conceptual designs, and we do the preliminary design. Then we perform static moving load analysis. Then we also perform seismic analysis based on the region. Then we perform detailed design. We perform the constructability check, and then we do the pier design, foundation, and if you want to perform solid structure interaction, we can do these in the software that we are working with. So here you can see we are using different softwares. I mean, the conventional approach is to use different softwares at different locations. So for preliminary design and static moving load analysis, we use software A. For seismic analysis, we use software B. Then we perform detailed design. If something is wrong, if it doesn't, it comes out to be not good, we make some changes in the model, or we make some changes in the design which affects the static and moving load analysis, and this way we keep on iterating until we get the final solution. And we use different softwares to check the constructability and to do the foundation design. But using multi-platform to design these type of bridges would lead to longer time in project completion, because you will have to use different softwares. And since a single engineer is assigned to perform the design, or a team is assigned to perform the design, they have to learn the interfaces of these different softwares. And it will have different model files for different softwares for different phases, which can lead to loss of data. It requires more manpower, and it leads to higher conservatism in the design. So basically, this is how it affects a company. It leads to lesser projects completion in more time. It leads to lesser degree of competency, repetition of work, and monetary effects. That's how. And since an engineer is supposed to learn different interfaces of the software, sometimes it leads to fatigue also, I would say. But to provide a solution to the engineers, we have included all these designs, analysis, etc. in Midas Civil, one software. So you will use one software to perform the preliminary design, the static moving load analysis, seismic design, detailed design, constructability check, pier design, PMM. You can obtain the PMM curve from Midas Civil itself. You can do the foundation design, solid structure interaction built into one software, that is Midas Civil. And what would be the benefits? They are pretty evident. You have the same model file for different analysis. You can perform static, moving, and dynamic analysis at one platform, which leads to no loss of data. You can capture the soil structure interaction, you can perform construction stage analysis, constructability check with ASH2L RFT 2012 are automated, and it leads to higher degree of precision, more optimized design. So when you have only one software to work, you need to learn only one interface, and Midas Civil's interface is pretty easy to learn, and you can complete more projects in lesser time. It leads to higher degree of competency, no repetition of work, and thus there are monetary gains to the company as a whole. And there are some additional benefits for using one single platform. You can generate the model automatically with the auto bridge modeling tools that we have. It has better graphical user interface, which will be easier to learn for the engineers. Improved graphics with CAD effects, and detailed stress check, pier crack analysis, and fiber model analysis are included in Midas Civil. Thus, you can perform detailed analysis and obtain the results for the same. Now here, I'm going to talk about a bridge that, let's say, we are supposed to design today, and it is a post-tensioned segmentally constructed bridge, which is constructed using a span by span approach. And the span length is 180 feet, the width is 33.6 feet, the number of lanes are 2, and we are supposed to perform moving load analysis as per ASH2L RFT, and the applied codes are for pre-stressed concrete design ASH2L RFT 2012, and for creep and shrinkage we are going to choose CBFIP 1990 version. And these are the steps that I'm going to follow. First, I'll do the preliminary design, then I'm gonna do the design optimization. So for preliminary design in Midas Civil, we'll define the material properties, and based on our experience or the span by 20, we can choose a cross section, and we can use the wizard of Midas Civil to automatically generate the model for us. So let us generate this model in Midas Civil. So I'm going to open Midas Civil one more time here. So I'm just opening Midas Civil, and I'm going to generate this bridge constructed using balanced span by span construction approach. And okay, here it is. I just opened a new model. Let's just save it. And I'll change the unit system from inches to feet. I'll go to structure. You can see there is nothing in this project so far. I'll go to structure. I'll go to balanced, the bridge constructed using span by span approach. I'm going to define 3 spans, and each span has the length of 180 feet. And then I'm going to define the cross section. So I have already put these values here based on the experience. And the joint and diaphragm values are also defined. Then I'm going to go to the tendon tab, and I'll click on OK, and it will generate the bridge model for me. Okay, so the bridge model is generated already. You can see the different stages are also modeled by Midas Civil Wizard, and it has 3 spans. Each span has a length of 180 feet. So basically now we need to define the moving load analysis, and then we can perform the design to make sure that this cross section is okay or not. So just to save on time here, I'm opening an analyzed model, and then we'll talk about, if the model is not good, we're going to talk about how we can make quick changes in the Midas Civil model itself to do the optimized design. So let me just open the analyzed model. So once again, if you have any questions while I'm doing this webinar, please feel free to post your questions, and I'll take up all the questions at the end of the seminar. Okay, so I just opened a pre-analyzed model for you. It has the same dimensions as you can see on the model view, and we have performed the moving load analysis as per ASH2L RFT, and we can quickly design this bridge as per ASH2L RFT 2012 edition, and we'll check the flexure strength. And as you can see here, it is not good at certain locations. So basically we have to modify the cross section at we have to modify the cross section so that it becomes okay as per the code. So we will do some iterations in the software itself. So right now you can see I did the design check, which is the step 2 as per AASHTO LRFT 2012, and since it turned out to be not good, I'm going to modify the cross section by reducing the slab thickness. So to reduce the slab, so once again we did the design check as per AASHTO LRFT and the section came out to be not good. So we will modify the cross section in the wizard and we will generate the model again and we will perform the design to make sure that it is fine this time. So once again I will use the same wizard that I just used. Okay, so once again I just opened an empty model in Midas Civil and I'm going to use the span by span construction wizard. The parameters will be same here in the geometry. In the cross section, this time I'm going to change the h1 to, let's say, 0.7 feet or 0.6 feet depending on your wish and your experience. You can change these values, and I'll keep the parameters of tendon intact and I'll click on OK. And once again the model is generated by the program, and to show you the results for this model I'm gonna open a pre-analyzed model once again. So once again this model that I'm opening right now, it has the same dimensions as we have here. So I just opened it and let me show the results of this model to you. Okay, so once again it's the same model. I'll just go to PSC design, result tables, flexure strength. So this time you can see the flexure strength comes out to be alright at different locations. There is no item in red here, so this means it does satisfy the code requirements. We can also check whether it is okay in stress or not. Here you can see it is not okay. So we can make further modifications in the model to obtain the optimized design. So I have another iteration step. So here you can see iteration 1 is complete. In the iteration 2 I'm going to modify the tendon number. Now to modify the tendon number, once again I will open the same model that I have been working with. I'm going to use the same wizard, and this time I'm going to change the tendon number. So here we have NS3. I can change it to 4 or 5. So this is just an example to show you how you can do optimized design with Midas Civil. And if it is satisfied under iteration 2, we can go ahead and do the detailed design. Otherwise we can do another iteration. While I was working with this model, I had to do 3 or 4 iterations to obtain the optimized design, and I did have some other iterations too, so that I can satisfy the different code procedures for the constructability and the final design. So this way I satisfied the design as per AASHTO LRFT. Now the benefits are that you auto generate the model. By using the wizard, the engineer doesn't, there is no fatigue. You can just create the model easily, and this way you can do the optimization automatically. It leads to quick and error-free modeling, and the tendon definition is automatically done, so you don't have to define the tendon every time you change the depth of the cross section. So let's say we change the depth of the cross section from 10 feet to, let's say, 9 feet. Then we will have to modify all the tendons which are there in the bridge, but since we are using the wizard, they are automatically done. And we can also take into account solid structure interaction. For this particular model, I did take into account the solid structure interaction. Let me very quickly share that model with you. So I'm just opening the model in which I have defined the soil structure interaction data. So in this particular model, I have defined the supports also, so that I can perform the precise analysis for considering the solid structure interaction, and I can also perform the seismic analysis on the same. So basically, Midas Civil wizard will be used to create the superstructure, but then the substructure can be manually created by the user. And this is how the model looks like. You can see I modeled the pier and the pier supports. I did not model the abutments, but if you want to model the abutments, you can also model the abutments based on your wish. Construction stage analysis is automatically obtained from the program. It automatically generates the construction stages, so we can check the constructability and obtain the camber diagrams. And the benefits is that it saves you time. There is single model file for static, moving, dynamic analysis, solid structure interaction, and construction stage analysis. It leads to simpler steps for design optimization. And you don't need to learn the different softwares, different graphical user interface to do the design. You can just work with one software. And you can do the detailed design after the optimized design has been done. And finally, you can do the pier design built into the software. You can obtain the PM interaction curve. You can check the pier section for cracking. You can obtain the moment curvature diagram. The fiber section analysis can be done. And this is how the result will look like. It will show you the 3D as well as the 2D PM interaction curve. So this is how Midas Civil can be used to perform analysis and optimize design of post-tension segmentally constructed bridges. And yes, indeed, just to make this webinar short, I did skip a lot of some steps involved in the optimized design, but the wizards that I've shown you, the functionality of the wizards, it's exactly same as what I've shown you in the webinar itself. So once again, if you have any questions for this webinar today, please post in your questions. We'll still have about 15 minutes left, and we'll take up your questions now. I have also put my contact details in the on the screen. You can, if you have any detailed question, you can send me the question on my email address as mentioned on the screen. Okay, there is a question from George. The question is, I have 5 spans with balanced construction. There are hinges in span 2 and span 4. How to add hinges if I am using the wizard? If you are using the wizard, first you will generate the model, and then you will additionally define the beam and releases to define the hinges at appropriate locations. So you will use the wizard to create the model, and then you will define the hinges by yourself.